All right, we're going to finish up the chapter today by talking about the applications for redox reactions. There's a lot of them, so let's get started. Number one is batteries. Batteries. Think about your life if there wasn't battery technology. All of the devices that you use almost depend on batteries. Hydrogen fuel cells. We'll talk about them briefly, but that's kind of a cool technology. Corrosion, huge part of electrochemistry. Combustion reactions, when anything burns, there is a transfer of electrons going on. It's a redox chemical reaction. Cellular respiration, you wouldn't be alive, or animals wouldn't be alive if there wasn't cellular respiration. Again, it's redox chemistry. Photosynthesis, plants wouldn't be here if there wasn't redox chemistry. Your nervous system, your nerves and how you feel and sense and respond to the environment depend on electrochemistry. So there's just a few that I could think of ways that we use oxidation reduction reactions in our labs. So let's get started. Need me to go back? Okay. Okay, so there's 7 applications. Okay, do we have it, guys? Batteries, hydrogen fuel cells, corrosion, combustion, cellular respiration, photosynthesis, and your nervous system. Kim? Well, we'll go through each one of them, guys, and you can write them down. So here we go. Batteries. We spent a lot of time in this chapter learning about batteries. In fact, you made a battery out of pennies. Washers, right? Copper, zinc. A battery is made by connecting electrochemical cells in series. What do I mean by in series? If you look at this flashlight up here, the flashlight takes 2 batteries. We hooked it up, they're connected in series, positive to negative, positive to negative. And if you hook it up in series, the voltage for each battery can be added together. So instead of 1.5 volts, now the flashlight is conducting how many volts? 3 volts. So you just add those together. And so we did that. We built a battery in here. Here's a battery, a car battery. Here's how car batteries work. You've got an electrochemical cell. One plate is lead oxide. The other plate is just lead. There's a pull of electrons from one substance to another. You hook it up in series. You add the voltage together. The electrolyte solution is sulfuric acid. That's why it's very corrosive. That on your battery terminals, if you clean them, that stuff is very corrosive. If you get it on your clothes, it can even eat a hole right through your clothes. So that's what's going on. And they're very heavy because they're filled with lead. Okay, alkaline batteries. I just wanted to quickly go over alkaline. Why are they called alkaline batteries? Is because they're made with potassium hydroxide. Hydroxide, OH minus, makes things basic. Another way of saying that is it's alkaline. So we call them alkaline batteries. But again, it's just electrochemistry taking place there. Okay, a hydrogen fuel cell. This technology is still getting better and better. They're not used a lot, but they are more and more. Let me kind of just go over what a hydrogen fuel cell is. It's a device that can produce some electrical energy. Look at what's used though. So H2, hydrogen gas, and oxygen gas are brought into this cell, and the electrochemistry takes place. It produces 1.23 volts of electrical energy. But what's cool about hydrogen fuel cells is the exhaust. What is the exhaust made of, guys? Hydrogen, oxygen, and water. Are those pollutants? No. So that's what's cool about hydrogen fuel cells. And maybe in the future we'll see more and more of them around. Okay, the big topic for today is this, corrosion. You're supposed to write down the definition of corrosion in your guided notes. So take a second to write that down and then we'll talk about it. So like it says, corrosion is the oxidation of metals. Think about this mnemonic that I've been saying the whole chapter, oil rig. What is oxidation, guys? Oxidation is losing electrons. So it's when metals lose electrons is when they are corroded or they're oxidized. Corrosion will cause metals to lose strength over time, and they become very weak. If you look down here at this metal pipe, this once was a very strong metal pipe. But look at it right now. You see all these holes in it, and it's been corroded. Another way of saying that is this metal has gone through oxidation, or it has lost electrons. Okay, this bolt and the nut that's on it have been corroded, and you'll see a bunch of rust on there. Why is this bad, guys? Why is the oxidation of metals bad?
Because it takes them away.
It makes them weak, but
Reduces them.
are you able to use them like you should be able to use them? I mean, maybe you won't, it gets so corroded that you won't even be able to use this bolt or take off the nut if you needed to. It makes them very weak. So it's a huge problem in industry, is corrosion. So we're going to talk about it in a few more slides and learn how to prevent corrosion. Rust. Okay, I guess I should talk about that. Rust is all of this red kind of red stuff on this bolt and the nut there. Rust is a product of corrosion. It's part of the corrosion of iron. When iron is oxidized, it forms iron oxide. Iron oxide is a fancy way of saying rust. Okay, so it's just the corrosion of iron. Okay, so why does corrosion occur? I want you to take out your reduction potential table. I've got it up here, but you can't really see it. But I want you to take yours out. We're going to I want you to put a box around oxygen right here. Okay? So put a box around this one here. That's kind of an important line on this table. The reduction potential for oxygen is higher than nearly every metal. There's only one exception. There's only one metal that's higher than oxygen on the reduction table. What is it? Gold. Gold is the only metal above it. Okay, well, what's the big deal? Why is that important to know? Well, let's go back to this table. Guys, if you're higher on this table, are you going to be reduced or oxidized?
Reduced.
So if you're higher, you're going to be reduced. If you're lower on this table, you're going to be what?
Oxidized.
Oxidized. And the oxidation of metal is what? You get corroded. It's corrosion. So why it's a big deal that oxygen is higher than nearly every metal is, where do you see oxygen at?
Everywhere.
It's in the air. Anything that's touching the air is going to be in contact with oxygen, correct? So will the air be able to oxidize all of these metals below it? Yes. And that's a huge problem, okay? The only metal that it's not able to oxidize is gold. That's what makes gold so valuable. One of the reasons it makes gold so valuable is it will last forever. It doesn't get corroded like other metals will. Okay. This means that most metals will be oxidized when it comes in contact with the air. We just talked about that. Iron is the main component of steel. And steel is used in building of cars, of buildings. Almost any construction item has some steel in it. And steel has iron in it. I want you to find where iron is on this table. Okay? Find out where iron is and let's put a box around it.
It's down low.
Okay? What is its electric potential? Minus 0.44. If most things are made of iron, is iron going to be oxidized by the oxygen in the air? Yeah. It will. And so That's a huge problem because most of the things that we have is made of iron. So it's very important to find ways to prevent the oxidation of iron. And there's a few ways to do that. We're going to talk about them now. Okay. So in an electrochemical cell made with copper and zinc, we did this in class. In fact, this is a picture that I took after the lab that we did. This is zinc, and this is copper. These are the strips that we put in our electrochemical cell. Which metal is being oxidized, guys?
Zinc.
Zinc. How do you know it's being oxidized?
Yes.
Yeah, it's lower on the table, but just by looking at it, how do you know? It's being corroded, isn't it? Look how this strip right here is almost, dissolving away and it's being eaten away. These were very thin. I should have taken a picture where I stood it up on end. And you can see that they're very thin. And so over time, this zinc strip will basically be dissolved away. Well, the copper strip obviously was being reduced. And again, this part that I'm outlining here was the part in the solution. And so it's being reduced. You're pulling in more copper atoms are being precipitated onto this strip. And it's actually thicker where I outlined it than it is down here. So you're getting more and more copper. So this gains mass. It gains electrons. And the oxidation, the zinc over here, lost mass and it lost electrons. Okay. Back to preventing corrosion. The primary method used to prevent corrosion is coating the metal with either paint or another metal. So you're either going to paint the metal or you're going to plate it with a different metal. Galvanizing. This is one of your vocab words and you're supposed to write down the definition in your guided notes. So take a second and write that down. Galvanizing is a process in which steel, again, steel is an alloy. It means it's a mixture of metals. Steel is mostly made up of iron, but there's other metals in it as well. So galvanizing is a process in which steel is coated with zinc to prevent the corrosion of iron. And I've got a couple of pictures down here. This is a new bucket, metal bucket, that's been galvanized. Has that shiny appearance, that lustrous appearance, because it's been galvanized. Well, here's a bucket that's been around for a while. We can tell because it's really corroded. All of the iron, a lot of it has been oxidized. And now it's very weak and it's really not useful anymore. So, galvanizing is the process of plating your metal with zinc. Now, why would we do that? Let's go back to your reduction potential table. Find zinc. Find zinc. Let me go back a couple of slides here. Let's find zinc on this table. Where's it at? Zn. Okay? It's right here. Is it higher or lower than iron?
Lower.
It's lower, so that means the zinc now will be oxidized, not the iron. And that's why they do it, is to protect that iron that's in the bucket here or in the material that you have. Okay, another way of preventing corrosion is using a sacrificial anode. Sacrificial means you're giving up one thing to protect another one, right? And so here's an example. If you had a steel pipe in the ground, it's gonna be oxidized over time. Well, it's gonna experience some corrosion. One way to protect that steel pipe is by using a sacrificial anode, this magnesium rod. If you hammered this magnesium rod into the ground and then connected a wire to this steel pipe, you're making an electrochemical cell where now magnesium is oxidized because it's lower on that table than iron. And so it's going to oxidize this magnesium rod. But what's easier, digging this steel pipe out of the ground and replacing it, or pulling this magnesium rod out and replacing it? Yeah, this is way easier. And so sometimes you'll see that sacrificial anode used as a way to protect metal. Okay, another example of this is on ships. They're always in the water. They can be corroded over time. The hull, the main structural part of this boat, you don't want it to be corroded or it will spring a leak. So what they do is they put a little zinc plate on there and they fasten that to the bottom of the boat underneath the water. You can't see them unless you take them out of the water. But look at all these zinc plates they put on here. Again, why are they putting zinc on there? Because it's lower on the table, which means it's going to be oxidized before the iron that's in the hull of this boat. Does that make sense? Kind of protects it. Okay, I've got a short YouTube video that we'll watch here. And it talks about corrosion. So please watch and see if we can learn something from this.
Let's think about cars for a moment. The car that you've had in mind was likely painted with your favorite color. The paint is not only there to make your car look pretty, but it has a more important purpose, to prevent rusting. When iron and steel are exposed to oxygen and moisture, rusting will occur. Rusting describes the corrosion of iron and steel. The term corrosion is used to describe the breakdown of a metal when exposed to the environment. When we say a metal corrodes, we mean that it has reacted with water and oxygen from the environment to form their respective oxides. We can demonstrate this using a simple experiment. Place an iron nail in 4 test tubes. Fill one with regular tap water until the nail is submerged. Fill another with regular tap water and add half a spoonful of sodium chloride, regular table salt. Shake from side to side to ensure that sodium chloride fully dissolves. Fill the 3rd test tube with recently boiled water and add a thin layer of oil. When we boil the water, we remove any dissolved oxygen, and the layer of oil prevents any oxygen from further dissolving. In the last test tube, add a spoonful of calcium chloride. Calcium chloride removes moisture or water. So in the first test tube, the nail is exposed to oxygen and moisture. In the second test tube, the nail is exposed to oxygen, moisture, and salt. So in the 3rd test tube, the nail is only exposed to water. In the 4th test tube, the nail is exposed only to oxygen. Stop.
Okay, so I wanted to pause the video for a second. If we numbered this, say this was 1, 2, 3, and 4, which nail do you think is going to get corroded or form the most rust? So make a hypothesis there, and then we'll watch the rest of this video. Okay, so let's see what happens.
Cover all 4 test tubes with a rubber bung and let stand for a couple of days. You will find that the nails in the 1st and 2nd test tubes have rusted. In particular, the nail in the 2nd test tube has rusted more than the nail in the 1st test tube.
Good, so if you said number 2, you were right.
Likely flaked off. You may see a reddish-brown precipitate at the bottom of these tubes. The nails in the 3rd and 4th test tubes have not rusted. So what has happened here? The iron has undergone an oxidation reaction, forming hydrated iron trioxide, or rust. Salt and acid act as a catalyst for this reaction, which is why the nail in the 2nd test tube formed more rust than the nail in the 1st test tube. Rusting can be very costly if we have to constantly replace these items made of iron and steel. Rust can be prevented if we paint the areas exposed to oxygen and moisture. This is done on many bicycles and cars. Another method to prevent rust is by placing a layer of oil or grease. This is done on many bicycle chains. It helps lubricate the moving parts, which reduces friction and slows down the rusting process. Another way to prevent rusting is a sacrificial protection method called galvanizing. Have a look at this reactivity table. Zinc is more reactive than iron. When exposed to oxygen and moisture, zinc will corrode faster than iron. So if we put them together, zinc protects iron but is sacrificing itself, hence the term sacrificial protection. This method is applied to prevent rusting on ships. The oxidation of zinc can be described using this following equation. So besides preventing rusting, there is another advantage to this galvanizing process. The formed zinc oxide layer can be removed, and the freshly exposed zinc can corrode once again, thereby further protecting the iron or steel hull.
Okay, so kind of cool, right? Hopefully you understood what was happening there. So we have now learned a few ways to prevent corrosion. If I ask you that on a test, and I will, what are 3 ways to prevent corrosion? Galvanizing, painting, oil works, like I said, grease. What about using a sacrificial anode? That's kind of what galvanizing is when you use zinc. Yeah. So those are all methods to prevent unwanted corrosion or oxidation of metals. Okay. I've got a couple slides here that show how the chemistry of corrosion works. Okay, let me see if I can explain it to you guys so that you can understand it. So we've got this metal here. This metal is iron. We have a water droplet. And we have oxygen in the air. Well, when oxygen comes in contact with iron, it oxidizes it to iron 2+. And then through a series of reactions can form iron oxide. Iron oxide is a fancy way of saying what? Rust. Rust is the product of the corrosion of iron. So most cars are painted. But if you have a car that has if it's dented a little bit, that paint kind of chips off and it exposes the iron to the air, and that's when you're going to see rust happening. That's when you're going to see that orange precipitate forming around that dent. And you've probably noticed that before. Okay? So, how do you prevent it? Use a sacrificial anode, zinc, since it's lower on the reduction potential table than iron, will be oxidized first. So they'll put some zinc by it. Instead of the iron being oxidized, now the zinc is oxidized. And then you can just replace the zinc. And the iron stays stable. Okay, so yeah, rusting is a huge problem because it can weaken building materials, or like this cable over time will become very weak. And some of the components of it, like this bolt, might not be able to be removed. You have to replace it. It costs a lot of money. And so we want to prevent corrosion of iron. We don't like to see rust on things. Okay, we're going to switch gears now. Instead of talking about corrosion, we're going to talk about the applications of redox reactions. Here's something that we haven't talked about yet in this chapter, but combustion reactions, when you burn something, this is a big part of our lives. There's a oxidation reduction reaction happening. So combustion reactions are redox reactions. I think, is this balanced, guys? Is this reaction balanced? Looks like I need a 2 there and maybe a 2 here. Is it balanced now? Yeah, I think so. Okay, if we look at a combustion reaction, what do you have to have as a reactant in order for combustion to occur? Oxygen. Can you have a flame without oxygen?
No.
No. This reactant is called methane. It's the main part of natural gas. Your furnaces in your house are burning CH4, methane. We didn't really talk about the half reactions of combustion because they're a little complicated because oxygen is split into two different molecules on the product side. But let me show you another way to track what the electrons are doing. If we kind of separate the reactant side from the product side, help me go through and assign oxidation numbers. What's hydrogen's? +1, I've got 4 of them. So what does the carbon have to be? -4. Oxygen by itself is what? Just by itself, free element is 0. Okay, let's go to this one. It's not by itself, so it's a -2, but I got 2 of them, so that's -4. What does the carbon have to be? +4. Oxygen is -2. Hydrogen is always +1. So if we look at the oxidation numbers now, I'm going to total them up for the carbon, hydrogen, and oxygen on both sides. For carbon, it's a -4. For the hydrogens, it's +1, but I've got 4 of them. So what is it total? +4. The oxygen's 0. So that's just 0. Okay, now let's do the product side. The carbon here is what? +4 now. The hydrogens, they're at +1, but I've got 4 of them. So isn't that +4? And the oxygens, -2, I've got 2 of them, so that's a -4. And a -2, but I got 2 of them, so there's another -4. So what's the total? -8. Okay, now I hope you can see what's happening here. What's happening to the carbon? Is it being oxidized or reduced? Its oxidation number is going up. That's oxidized. Which one is being reduced? The oxygen is being reduced, and we didn't do this with our half reactions because the oxygen was being split, and that makes it a little more complicated. But I think we can track the electrons pretty effectively using this method. How many electrons were, okay, let's go back to oil rig. Since carbon is being oxidized, it's losing. So how many electrons did the carbon lose? It lost 8. It lost 8 electrons. Stay with me, guys. It's a little complicated, but I think you'll be able to see it pretty easily. Oxygen was being reduced, and reduction is gaining electrons. How many electrons did the oxygen gain?
8.
It gained 8 electrons. And guys, this is why oxidation and reduction have to happen at the same time, because the carbon lost its 8 electrons and gave it to who? The oxygen. It gained those 8 electrons. And so whenever you burn something, there is a transfer of electrons that's happening here. Your fuel source is oxidized. The oxygen is gaining those electrons, so it's reduced and it forms CO2 and water. Anytime you burn something. Okay? And so that's kind of cool to see that. Carbon is oxidized, oxygen is reduced. Here's one of the most important chemical reactions on the planet. Okay? Cellular respiration is a series of reactions that allows animals to obtain energy, including us, right? If you guys remember back in your biology class, what is this molecule called? Sugar. More specifically, what's its name? Glucose. Well, glucose is in almost every food we eat has glucose, and our metabolism breaks it down into the simplest form into this molecule. Well, inside our mitochondria, this glucose is oxidized. It's reacted with oxygen. Where do we get this oxygen from? The air. That's why we breathe, right? Is to get oxygen. And then it makes CO2 and water and provides us with the energy that we need to live. Let's go through. I know this is a little bit long and it's sometimes you lose focus, but stay up here, watch what we're doing. Let's assign oxidation numbers and see where the electrons are doing in cellular respiration. What's the oxidation number for oxygen, guys?
-2.
-2. I've got 6 of them, so that's a -12. Hydrogen's plus 1, but I got 12, so that's plus 12. What's the carbon got to be?
Guess it's 0.
0. Good job. Oxygen by itself.
Minus 2. 0.
By itself, free element is 0. This is good review. Oxygen is not by itself. Minus 2. Times 2 is minus 4. What does the carbon have to be?
Plus 6, though.
Plus 4. Well, we'll do that later. We'll do that later. Oxygen, minus 2. Hydrogen, plus 1. Let me erase those totals down there. So let's find out what the electrons are doing in cellular respiration. Now let's go through and calculate for carbon, hydrogen, and oxygen on the reactant side and the product side. Carbon, 0, right?
Yeah.
Hydrogen's plus 1 times 12. What is that? Plus 12.
Minus 12.
My oxygen's minus 12 plus 0 is what?
Minus 12.
Minus 12. Carbon's, what's plus 4 times 6?
24.
Plus 24. Hydrogen's, what's 1 times 2?
2.
It's 2 times 6.
6. 12. 12.
Isn't that plus 12?
Sorry, I was
So-
thinking 1 times.
Plus 12. Now let's do the oxygen. It's a little complicated because they're split, but let's see. I think we can do it.
Minus 4.
What's
times
12 times a minus 2?
24. Minus 24.
Minus 24. But then we've also got some oxygens here. What's 6 times minus 2?
Minus 12.
Minus 12. And what's minus 24 minus 12?
36. Minus 36.
It's equal to minus 36. Okay, now stay with me because this is where we're going to track the electrons. Carbon saw its oxidation number go up. So that's what?
Oxidation.
Oxidation. An oil rig is oxidation is loss. How many electrons did the carbon lose?
Hold on. 24.
It lost 24 electrons. Well, if it lost it, somebody had to gain it. Who gained those electrons?
The oxygen.
The oxygen. How many did it gain if it went from minus 12 to minus 36?
24.
Yeah, it gained 24 electrons. So the oxygen here was reduced. So when you eat food, guys, the food is oxidized. So that food is providing the electrons that give us the energy that we need. Why do we breathe oxygen, though? It should become apparent. Why do you have to breathe oxygen? So that it can accept those electrons that were lost from that we got from the food, right? Because something has to gain it. If the electrons are being lost, something has to gain it. And so, hopefully that makes sense. I've got a quick slide. Let me see if I can explain this. I know this is kind of biology stuff, but there's chemistry and everything. In fact, when you go to college, you can take biochemistry classes, which are really pretty cool. What's the mitochondria, guys? You learned in biology, everyone says it's the what? It's the powerhouse of the cell. Because it makes all the energy, right? How do we get energy, guys? Well, we get it in the form of this molecule, ATP, adenosine triphosphate. It's made in the mitochondria. How is it made? Well, it's made through a series of redox reactions. These reactions that we learn about in this chapter are right here. This is the electron transport chain, the last step of cellular respiration. This is where we get most of our ATP. How come we have to breathe oxygen? Well, oxygen's right there. It's found we breathe it in, it goes into our lungs, it goes into the red blood cells, where the red blood cells take it to every cell in your body, and it ends up in this structure, this organelle called the mitochondria. In fact, it goes right into the middle of the mitochondria, and here's what happens. The oxygen is responsible for taking these electrons. It's called the electron transport chain. It takes these electrons and it accepts those electrons. It's called the final electron acceptor. When you gain electrons, what do we call that? Rig. Gaining of reduction is gaining electrons. So the oxygen is reduced and it forms water, the very last step. Now, if you don't have oxygen, can anything accept these electrons? The answer would be no. Everything backs up. Do you make these ATP anymore? No. And so that's why it's so important to breathe oxygen. I mean, seriously, stop breathing. How long would that take? Until something serious happened.
Are you serious?
No.
5 minutes.
You're going to see a cell death happening within minutes. Cells can't live without ATP. And you can't get ATP unless you breathe oxygen. Okay? Hopefully you can kind of see the importance of redox chemistry, even in biology. It's kind of interesting. Okay, I know this is getting quite long, but photosynthesis. Another equally as important reaction as cellular respiration. This is how plants get energy. Guys, would we be here without plants? No. What do plants give off that we really like? Oxygen. If you look at the chemical reaction for photosynthesis, you see that glucose and oxygen are made by plants. How does this chemical reaction relate to cellular respiration? Isn't it basically just flipped?
Yeah.
The products of photosynthesis, glucose and oxygen, aren't they the reactants of what we do, cellular respiration? So plants give off what we need. And we give off what plants need. Isn't that cool? And so we could go through and track the electrons here, but it's just the opposite, so I don't think we'll spend much time doing it. But the carbon is reduced. Carbon from CO2 in the air that plants get is reduced to make glucose. And the oxygen is oxidized. The oxygen is turned into molecular oxygen and released into the atmosphere so that we can breathe it, right? And this diagram shows this. Light's coming in, CO2 is coming in. CO2 makes sugars, C6H12O6. It gives off oxygen into the atmosphere, and plants need water. Why do plants need water, though? The water goes to the chloroplast, and the water is actually split. It's kind of an electrolytic process. It needs energy, but it gets that energy from the sun, and it splits water into oxygen and hydrogen. It doesn't use the oxygen, it releases it into the atmosphere, but it does use the hydrogen and the electrons that it gets when it does that. And so water the oxygen is oxidized and the carbon is reduced. Okay. Here's another really cool part or application of electrochemistry. The nervous system is made up, if you look up at this picture right here, your nervous system is made up of two parts. The central nervous system, which is the brain, and the spinal cord. And then there's another part called the peripheral nervous system, which is all the nerves in your extremities, your arms and legs and so forth. Everything except for the brain and spinal cord. Nerves. Why are they so important? What do they do for us?
They help us feel.
Yeah, they sense the environment that we're in, right? But they also help us do what? React to the environment. We move, we breathe, we think. Everything that you have done in your life started with neurons. This is a neuron. It's a nerve cell. It's made up of two parts. You have a dendrite where the signal comes in to the dendrite, and then it's transferred along this long tail called the axon. And then there'll be another dendrite over here, and these cells communicate to each other. Every time you move, millions of neurons are communicating with each other. And every thought that you've ever had in your life has started by neurons, sending signals to other neurons. And it's amazing. If you look at this picture right here, it just shows, one neuron connected to thousands of other neurons and these connections that you build. And that's how you learn. And that's how you form memories. And it all works by electrochemistry. So let me see if I can give you a brief kind of overview of what's happening here. Okay, this is a neuron. This is the dendrite. So there's a signal coming in. Say you want to move. Well, you've got to think about it, and then the neurons have got to send signals, and it's got to go through all those neurons. Well, it's electrochemistry. If you look down here, this plus 30 and this minus 60, this is a potential. It's actually measuring in millivolts, MV. When a signal comes in, these sodium ions, which is Na+, has a positive charge. When the signal comes in, it tells the neuron that these sodium ions are going to move through these sodium channels here into the neuron. And it makes the inside of the neuron more what? Positive or negative?
Negative.
If it's got positive ions coming in, it's going to make it more positive. And so you'll see this threshold right here, it's going to jump. It gets more positive, and that sends a signal down this neuron here, and then this part of it will rush in, and then the sodium atoms here will rush in, and the sodium atoms here will rush in. And that's how they communicate with one another. It's electrochemistry. Positive, negative charges. And so it's just amazing to me to think that everything that you've ever done in your life started with electrochemistry at the nervous system, the neurons. Anyway, there's a whole bunch you can learn about this. It's really cool. You take anatomy and physiology, you'll learn about action potential, propagation, and how they really work in more detail than that. But, very cool. Okay, I'm going to finish the lesson today with this review video it's a YouTube video. It's put out by Crash Course. They got a lot of good videos, not only for chemistry, but every other subject you could think of. And they just make short videos that kind of summarize things. I wanted to show you this for a couple of reasons. Number one, I want you to review the chapter this way. Number two, I want to show you how much you guys have learned. Everything on this video we have talked about. So when he talks about all this stuff, I want you to remember us talking about it and learning about it, and it's a good way to review. So anyway, I hope that you like this video.
The controlled flow of electrons making possible laptops, and phones, and cars, and pacemakers. Batteries, just like everything else in life, is just chemistry raised to the power of awesome. The kind of chemistry that happens inside of a battery is called electrochemistry because it involves reactions that produce or consume free electrons. Specifically, they are oxidation or redox reactions, the ones where electrons are exchanged. I've told you about redox reactions before, and if you haven't seen that episode yet, you should probably go watch that before you watch this. Don't worry, I will still be here when you get back. Now, when the flow of electrons from these kinds of reactions are sent through a conductor, like a piece of metal, it can be used to do all sorts of work. Like, for example, this kind of work. The amount of work that can be done depends on how strong the push or pull on electrons is between the two reactants. This is the reaction's electrical potential, but to its friends, it's known simply as voltage. Basically, if the voltage is high, each electron can do a lot more work than if the voltage is low. Many of the wonderful things in our modern lives are based on one simple premise: putting a device between the two halves of just such a reaction, the half that donates electrons and the half that accepts them. By harnessing that energy, a lot of the coolest things you've done today, up to and including watching this episode of Crash Course Chemistry, has been made possible. Part of what makes redox reactions so powerful and powerfully excellent is that they are complicated. Because in each reaction there's at least two things going on. There's a part of the reaction where the electrons are being released and another part where they're being eagerly demanded. So when we deal with electrochemistry, we usually think of reactions in terms of half reactions. Let's start with the typical redox reaction that happens in this alkaline battery as an example. In here, elemental zinc is going to react with manganese dioxide, also known as manganese 4 oxide, to produce manganese 3 oxide and zinc oxide. When you break this down into half reactions, first you have elemental zinc with an oxidation number of 0 being oxidized to zinc 2 ion. At the same time, manganese 4 is being reduced to manganese 3. When we balance the half reactions, we see that 2 electrons are released during the oxidation of each zinc atom, and 1 electron is consumed consumed by each manganese 4 atom. The water and hydroxide ions, by the way, come from a solution of potassium hydroxide, which is a basic or alkaline compound, which is why we call these things alkaline batteries. Now, if each of these half reactions occurred in contact with the other one, they'd just spontaneously go to equilibrium, releasing energy as a bunch of heat, which wouldn't be very helpful. So batteries are designed to harness that energy by isolating the half reactions from each other. This allows excess electrons to build up in the negative terminal, called the cathode, while an electron vacuum of sorts occurs in the positive terminal, the anode. Electrons can then cross from one half reaction to the other only when we connect the cathode and the anode of the battery via conductors, so the current can be used to do work, which I can do by licking this 9-volt battery. In these batteries, the zinc is in the center, surrounded by a layer of cellulose that allows ions to pass through. The manganese oxide is in the outer layer that surrounds the zinc core, but the cellulose barrier doesn't allow the zinc and the manganese to mix. Alkaline batteries are a type of galvanic cell, which is generally defined as an apparatus that generates electrical energy from a redox reaction. Here's another example of a galvanic cell, one where the interesting part is the flow of whole ions instead of the flow of electrons. In this case, wires connect metal rods that are suspended in a solution. They're the anode and cathode here. What's noteworthy is that the metal atoms are actually consumed. They're used up from the anode rod as they're oxidized, and the metal slowly wears away. Meanwhile, the opposite happens at the cathode rod, where metal ions from the solution gain electrons and precipitate onto the cathode as pure metal, gradually growing larger. The circuit is completed by the wire, but also by a salt bridge, which is often a U-shaped tube that contains a salt solution that allows the metal ions to go from the anode to the cathode. So, now you know how batteries work, developing and transferring a charge using electrochemistry. But before any redox reaction can be used to text your boyfriend or girlfriend or whatever, we need to know how much voltage it can generate. Fortunately, all of those amazing chemists who have come before us have done a lot of the work once again. The voltage generated by many half reactions is already known and can be found in most textbooks or online. And as I mentioned earlier, voltage is really just a way of expressing the electrical potential of each half reaction. The difference between the chemical demand for the electrons in one half versus the tendency to lose them in the other. These measurements are done at standard conditions, which we discussed in the enthalpy and entropy episodes, and by convention, they're written as if the substance is being reduced, not oxidized. For this reason, the value is known as the standard reduction potential of a substance. To see how reduction potentials work in half reactions and combine in an overall reaction, let's consider a galvanic cell where zinc is oxidized and copper ions are reduced. Keep in mind the potentials are determined at standard state, 25 degrees Celsius and 1 molar solutions of the copper and zinc ions. Our cell needs to be set up under the same conditions, or the voltage will be a bit different than expected. The half reactions show more clearly what the electrons are doing. We can see that the zinc is oxidized and the copper is reduced. Now, all standard reduction potentials are measured relative to the reduction of hydrogen ions to hydrogen gas, which is set at 0. Just as a baseline. When copper is reduced, for example, it generates 0.34 volts more than hydrogen does. So we say its standard reduction potential is plus 0.34 volts. The standard reduction potential for zinc is negative 0.76 volts, but because zinc is oxidized in this reaction, we can't use the reduction potential directly. Instead, as a general rule, when you convert a reduction half reaction to oxidation, the sign of the voltage is simply reversed. So the negative 0.76 volts for the reduction potential of zinc becomes positive 0.76 volts for the oxidation potential of zinc ions. And the electrical potential for the whole reaction, called the standard cell potential, is just the sum of the standard potentials of both half reactions. In this case, that would be 1.1 volts. Now I gotta point out here that the electrical potential of a redox reaction is related to its equilibrium constant. There's actually a way to determine the equilibrium constant from a measured voltage and vice versa. Both of these constants have a lot to do with the energy that the reaction can release, or its Gibbs free energy. But in brief, the higher the voltage, the more electrical energy can be produced. So if the voltage is positive, it means that under standard state conditions, the reaction will spontaneously go forward. If the sign is negative, the reaction will proceed backward. And it totally makes sense. When you think about it, that reactions like this are used to make battery cells. The reactions in batteries need to be spontaneous because their whole purpose is to release energy, not consume it. So what if we don't want to power a phone or a laptop or a toy shuttle? What if instead we want to plate an iron car bumper with chrome? This cannot be done with a spontaneous reaction. Instead, a different electrochemical process is needed, one that you've probably heard of: electroplating. This is done by immersing an object in a solution that contains an excess of ions of the coating metal. A bar of the coating metal, in this case chromium, is used as the anode, and the item to be plated, the iron bumper, acts as the cathode. When an electric current is applied, a redox reaction occurs in the solution and atoms of the coating metal are deposited on the cathode. This is essentially the opposite of a galvanic cell, known as an electrolytic cell, and it performs electrolysis, which uses electricity, electro, to do the breaking apart, lysis. In this case, molecules in the solution are being broken down so that the metal atoms can be deposited on a surface. Electrolysis is used for lots of other things too, like coating jewelry or flatware with gold or silver, refining metals, and separating mixtures of metal ions. Also, converting water into hydrogen gas and oxygen. So if you didn't already understand how much impact chemistry has on our daily lives, you certainly should be able to see it now. Not only are all of the materials around you made of chemicals, but even the electrical devices that power our lives depend on the reactions of electrochemistry. Thank you for watching this episode of Crash Course Chemistry. If you were listening, you learned that
Okay, so I think that's a good video. I just wanted to point out, this is all the stuff, this is all the stuff that you talked about. I want you to think about, did we talk about electrochemical reactions in
Yes.
here? Did we learn half reactions?
Yes.
Did we learn how batteries work?
Yes.
Galvanic cells?
Yes.
Calculating voltage?
Yes.
Standard reduction potentials? Standard cell potentials? I mean, we talked about everything that he talked about. And so, we've got to the end of this chapter. Hopefully, I want to go now is to your student workbook. And I want you to complete the electrochemical cell worksheet number 1 and electrochemical cell worksheet number 2. And that's it for this chapter. Hopefully you've learned something about electrochemistry.